So hi everyone, my name is Reda. I've been building CPSR-Lite rollup. It's a Solana DeFi rollup. Today I will show you a proof of concept how we can take messy steps, DeFi flows, and turn them into just a few transactions that are more reliable and cheaper. So right now, DeFi flows on Solana are fragile. For example, when I do swap, then add liquidity, then stake, each action become a separate transactions. Every extra step is another chance to fail. When network is busy, popular pools get locked. Two people try to touch same accounts and both transactions clash. We end up retrying again and again. That's we call retry hell. And on the top of that, we overpay in fees. So CPSR-Lite rollup fixes this problem by three things. It reorders steps so that transactions don't clash over the same account. It's make multiple steps together into fewer transactions, less overhead. And thirdly, it size fees correctly by simulating once, learning the real cost, and paying only what's needed. Think of it like turning 6 separate Uber rides into 2 carpools that don't fight over the same road, and we do a short test drive before we actually go. So how it's work? So firstly, we start with attend. They are the instructions. So we take the steps the user wants. Then we build a DAG. A DAG is a directed acyclic graph. We detect account conflicts and create an order when needed. That gives us a clear deterministic plan. Thirdly, we extract layers. We groups. It's a groups of steps that can safely run in parallel. Then the chunking part is coming. We pack each layer into transaction sized bundles under Solana limits. So that's include the method size, accounts, instructions, compute. We can also use lookup table to fit more. And after the chunking, we go forward to the OCC capture. So we snapshot the accounts will touch, including a hash of their data and slots. This ensures that the word doesn't change it too much before we send. And the fee planning, we simulate once the real, we read the real compute units, then set a tight CU limit with a smaller buffer. And lastly, we execute. We sign and send only when everything is consistent. So that's give us fewer collisions, fewer transactions, lower fees, because we plan first, then execute. So what is the DAG? DAG is the brain of the planner. On Solana, if two transactions don't touch the same account and one writes, they can't run together, the account is locked. So we first turn user steps into a DAG. Each edge means this step must run before this step. For each account, if there are writers, we order them deterministically by priority, then by index. And pure reads don't add edges because they are just reading from the account. And we union all of this together, and we have a deterministic DAG. From the DAG, we get a topological order and layers, and we set a steps that can run in parallel. Like example, if both are read, they can run parallel. If one write and the other read, the writer must go first. And lastly, if both write, we enforce a stable order. So the first one write, then and second need to wait for him. Why that it's matter? So we remove the randomness from contention, and writers are related on purpose, and we get same input. It's equal to same plan and fewer retries. It's like a basic kitchen that sous chef can't use the same oven at once. The DAG is our schedule to avoid collisions, while other prepare continues in parallel. And after the DAG, we have the chunking part. We pack transactions. So the goal of it's fit as many steps as possible into each Solana transactions without breaking limits. So we need to respect message size and bytes, number of unique accounts and abstraction counts, and compute units. How it's work for each attempt, we calculate its footprint, including bytes, key, CU estimate. And after that, agree the accumulator, try to add it. And lastly, if adding would exceed a limit, we close the chunk and we start a new one. So the result is gonna give us each layer turn into a few packet transactions, and we can have multiple layers. And after that, there is the OCC part. It's optimistic concurrency control. Before sending anything, we do the OCC. So we take a snapshot of the exact account we'll touch. So we don't send transaction based on stale data. So steps collect the target account, fetch their states, including Lamport's owner data and slot, and create a lightweight fingerprint using a short hash of data. Store this fingerprint with the transaction plan, and if the slot drifts, if the slot drifts is too wide, we retry with backup. So this avoid the common issue that's called it's worked in simulation, but if it's failed on chain. So yeah, and before the last part, we have the fee serialization in sending. We use fee oracle by default. It's enforce caps and floors, so never too high, never too low. About serialization, we build transactions message with payer, block hash, and fee plan, and we add compute budget abstractions, and we compile a V0 message and enforce a packet. We enforce Solana packet size, and lastly, we have the sending part. We simulate once, read actual compute units, then apply a safety buffer, and rebuild with final CU limits and verified block hash in send. Why it's work? We don't guess compute. We measure it. We size packet correctly before sending. We avoid overpaying for priority fees. I will do right now a demo for what I reached until now.
Yes, Vector, you're next. Oh wait, hold on. Go ahead, Reda.
Yeah. So about the demo, I'm just having. Give me a second. Yeah, this is the command. So right now, what I'm running a mix. It's a mixed demo. It's make 3 memo that are read only, no conflict, and 6 transfer same address, which are conflicts. So this way we can see both parallel work and forced ordering. I'm waiting to transact to the command be run it, and I will explain what is the output. Okay, yeah. So firstly, like you see here, we have 14 attempts, and the planner tag, the DAG planner build a conflict graph and then group steps into layers that can run together. Like example here, there is nine steps in this layer, and all other ones are transfers because we can't combine them with read. And we have 6 chunk here. So we packed the 9th operation from layer 0 into 1 big transactions. Then 5 transfer each become their own transactions. So instead of 40 separate transactions, the rollup only sends 6 separate transactions. And here, like, I'm gonna explain this part. So on Solana, every transaction has a fixed base fees. It's think of it like a ticket price. So it's about 5,000 Lamports. It's about 5,000 Lamports. We have 40 transactions. That's mean 40 tickets. If we multiply 14 on 5,000, we're gonna get 70k Lamports. But when we separate all those 14 transactions into chunks, we just get 40k Lamports. So we reduce the cost by 57.14%. So we reduce the cost, and that also will reduce the transaction failing. And yeah, this is what I did until now. And also I'm storing some information here about the execution. So In the next 2-4 weeks, I will try to plug in real adapters, a swap, a liquidity pool, and a stake using the adapter API. And I will switch on a dynamic fee oracle, so we aim for a target confirmation time. I will also add an alt manager to support bigger bundles, and I will harden the code with more tests and metrics. And after 4 or 8 weeks, I want to get success rate of 95% for passing transactions. So right now 15% transactions are failing. I want to make it 95 and reduce the compute budget by 60% or 30%. Yeah, I'm a little bit ambitious, but yeah.
Ambitious is good, man. I think this is ambitious to begin with, and how far you've gotten in 6 weeks is remarkable. Really great work.